I'm happy to help you with the harder problems, and I'll skip over the easy ones. So let's take a look here. I'm happy to start from the beginning, unless there's a particular problem you're stuck on the e-quiz. Yes? Let's take a look here. I remember pausing on 16 as well. Yeah, let's take a look at that. This was a hard one to go through. So let me zoom in a little bit here so we can view this on the screen a little better. Here's the problem we're given, and this is a little tougher problem because I've got two. I'm going to zoom out just a bit so I can see that on one line. We've got two recursions happening. And so let's examine this function because it's on several questions here. So, what's that? Yes, I am. I'm recording this. So, here's question 16. I have a function, takes m and n as parameters. They are integers. Notice the base case. The only time we stop is either m is equal to n or n equals 1. Now, that's simple enough, but the kicker is, whenever I'm calling this, both recursions better not be infinite or I've got a problem. Here, this recursion, m and n will decrease by 1 as I recurse, solving the problem. If this case is not true, n and m will both decrease. If this will recurse to a point where either, well, at this point, if m is equal to n, this will be done. I won't worry about this. So if I got past here, then I know m and n are not equal. The only way that that's going to end is either n turns into 1 at some point, and this becomes true, or m and n then will eventually be equal. But the problem is, if they're not equal now, this will never result in m being equal to n. So in this case, n better be greater than 1, or I've gone past 1, and this will recurse forever. So just looking at isolating our problem, just looking at this recursion, if m and n are not already equal, the only thing that will stop this from recursing forever is n better be greater than 1, greater than or equal to 1. And if it's equal to 1, I wouldn't even got here in the first place. Yeah. No, if it's equal to 0, we got a problem. Yeah. And that's why I avoid the exact equal. I like to do the greater than or equals in these end cases. So just looking at, and see how we're looking at this problem. We're breaking the pieces. Just look at this recursion first. This will never end unless n is already greater than 1. It will end if n is equal to 1 because it won't even get to here. Okay, so that recursion, n must be greater than or equal to 1. Now let's look at this recursion, because one of them must eventually stop if I get past this. Well, both of them must eventually stop, right? If this never stops, I've already got infinite recursion. I don't even have to worry about what this is returning, because this has never come back. Now, suppose this does not infinitely recurse. Is there a different condition here? Let's see here. Well, notice in this recursion, n is never getting smaller. So if I've gotten to here, I know that n is not equal to 1 at this point. And we know that if n is not greater than or equal to 1, I'm already infinite here, so it won't matter what this is. So n better be greater than or equal to 1. Okay? And at this point, we know that if I've gotten here, n is actually greater than 1 if I'm recursing here. So assume n is never is greater than 1, so this will never be true. What will cause my recursion to end? Well, when m is equal to n. So this one what does m have to be? It better be greater than or equal to n. Otherwise, as m decreases, if it's already less than n, this one will recurse forever. Because n is never going to reach 1 because n is not decreasing in this recursion part of it. So see, breaking up the problem, just looking at, okay, when I recurse to this point, it needs to end when n hits 1. This one better end when m finally gets small enough to be equal to n, because n is never decreasing in that recursion. So break it into two pieces leads me to the solution m better be greater than or equal to n, and n better be greater than or equal to 1. Or one of these recursive functions will go on forever. Even though one of them may end, the other one also has to end. Otherwise, because I'm calculating both. So I can't just say, oh, if n is 1, I'm done. Or if n is 2, doesn't matter what m is. Well, this one will end, but if this one never ends, it's calculating this and coming back with some answer, and then saying, okay, I need to now add the answer to this, and this has now gone on forever. So you have to consider both cases and separate them. Just think, okay, when I calculate this, that better end sometime. And okay, if that does end at some point, this also better end. And if n is not 1, then m better be greater than n, or this will go on forever. Because the only two conditions that stop it are when m is equal to n or n equals 1. Now, you may call this 2 base cases or 1 base case. It's not a big deal, because I could have this be 2 statements. It could be if m equals n, return 1, and then if n equals 1, return 1. It's just more compact. I can say if one of these are true, this will return a value. So when they ask is there 1 or 2 base cases in a few questions, that's not such a big deal. Any questions about that? This was probably one of the harder questions in that quiz. All right, I'll go back to the first one and just walk you through them and think through the logic here, and maybe you can help me out. This one should be fairly quick. Let me zoom in a little bit more for you. Which is not iterative? Do while, recursion, while, or for? What do you think? Yeah, recursion. A while I kind of think of that's possibly less iterative because the condition is not necessarily an iteration, but recursion is definitely not iterative. Okay, so I'll just go ahead and mark that. Question 2. Now this is one that I disagreed with the answer the author gave in the initial form of this. If A calls B, we got 4 methods, A, B, C, and D. If A calls B, B calls C, C calls D, and D calls A, which is indirectly recursive? I think all of them is the best answer. In the book, or the author's answer was A, but I'm thinking, wait a minute, what if I call B? Unless you would say B is only called by A, then I would say, okay, then A is the recursive. But it doesn't say that here in the question. It just says A calls B, B calls C, C calls D, and D calls A. You've got a loop going, and if there's another method that ever calls C, and we know that C will call D, and D calls A, D calls B, and B calls C, then C is also indirectly recursive. So I updated the key, put all of them are recursive. Unless you add the extra statement, the program only calls the function A, the main program, and B and C only ever get called by A, then I might say, okay, then A is the one that's indirectly recursive. So if there were more information, then I would say, okay, A is the best answer. But when they don't say that, we just know that they essentially call each other in a loop. Then we've got a indirectly recursive. Doesn't mean it's infinite. because if there is some condition that changes as the calls are made, it doesn't necessarily mean it's an infinite recursion. Now let's examine this one. The statement we're looking for is, which is the base case? So don't even worry about what the function returns yet. There'll be other questions about it. All we care about this particular question is, what is the base case? And remember, whenever we're looking for the base case, we're looking for what conditions will end the recursion. So those are the two lines that determine when the recursion ends. So the base case is lines 3 and 4. Statements in lines 3 and 4. The second half is a lot of true and false, and they're pretty quick. So it does let you resume it. Yeah, I thought it let you resume it. At least it did for me. I thought I set it to be resumable. Yeah, no time limit and resumable. That should mean that you can start part of it any time and then come back to it. And remember with these e-quizzes, open book, you can take them with your friends. It's more of just making sure you've gone through the answers. It'll be more helpful if you think through it than just have your friend tell you what all the answers are, of course. But that's up to you. Okay, so we've got this definition. If number num is greater than or equal to 10, we return 10. So there's our end case. And otherwise, return, let's see, the number times the next number plus 1. You might think here, wait a minute, num is increasing. I've got infinite recursion. Not quite, because notice our end case, we're checking when number gets bigger or equal to 10, it will stop. Now we're looking for, if I give it an 8, what will it return as a result? Well, now we act like we're the processor. Here we are, we have 8 for number. Skip that because it's not greater or equal to 10. I return number 8 times whatever this has when it has a number 9 in it. Well, I know it will be 8 times 9, and then times, well, if it's 10, it will return 10. So 8 times 9 times 10 will be the value returned by that function. And then down here, I see 8 times 9 is 72, 9 times 10 is 720. Any questions about that? How we got 8 times this taking 9. Oh, it returns 9 times the next thing, which would be 10, returns 10. 8 times 9 times 10. Okay? Okay, let's walk through it again. I give it an 8. Num is 8. So let's think through here now. And we could even take a little notepad if it helps. And we'll draw it out. That's what I like to do. If I ever get stuck, grab a piece of scrap paper and think through the steps. All right, so we have rec func given an 8. Well, it's going to return, it's not returning 10, so it's going to return 8 times rec func of 9. Okay? 9 is going to return 9 times rec func of 10, which is going to give us 10. So 8 times 9 times 10, then there's my result. I'm multiplying them together. So writing it out, perfectly fine. Don't be embarrassed to have a little piece of scratch paper and say, okay, here's what I did. And as you do it a few times, the key thing here is to notice I'm doing the multiply. Sometimes you're doing a plus, sometimes you're doing something else. And remember when you're multiplying, if I ever am multiplying something that ends up being 0, everything else, no matter what I've multiplied by, gets multiplied by 0. So 720. Now here's the same one. Now they give us a statement. Print line rec func of 10. Is it gonna infinitely recurse, or is it gonna give us an answer? Well, yeah, it should just be 10. Now, when would it go? Would it ever go infinite? If I give it an 11, does it stop? Yeah, it'll stop it. It always returns 10 if I give it anything bigger than or equal to 10. So that's why greater than or equal, whenever you do a comparison, that's a safer way to help guard against the horrible infinite recursion. You know that if it's integer, even if it's a very large negative integer, it's getting bigger and will eventually be greater than or equal to 10. If you only have the equal 10, equal 10, if you give it 11, it's going on forever because it's never equal to 10 anymore. Now this one's a little more complicated just because it has a few more parameters, but don't let that intimidate you. As you look at a few more parameters, it only means just a little bit more to keep note of, but as you look at the function, your parameters, I can't get that, grab that corner and resize that window, and alright, forget it then, there, trying to make that just a little bigger. It takes an integer array, that's a list, and I have a first and last, so we have to think through our little array knowledge from the past. If first is equal to last, then I'm returning the element of the array at that position. Otherwise, I'm returning the element in the array at position first, plus recursion to the same list, passed as a parameter, and the same last parameter passed. So the only thing that changes in the recursion is first is getting larger. So now let's see what's the question they're asking about this. Given this sequence of numbers in the array alpha, I have an array here, I'm asking, oh, what is the result giving it that array with 0 for the first number and 4 for the last number? Okay, so 0 and 4 are first and last. And I see that what I'm doing is, wherever I am at first, I'm going to add the next result of this, which will be first getting bigger, so it'll be the next element, and the last is still staying the same. So as we look at this, we can see I'm adding each element to the next element in the list until I get to that index of the last element. So I'm adding up from first to last. Now I can either write out the numbers as I go, or just see I'm going to add that to the next one until I get to the last. So now I have to remember, what was it asking for? First element is 1, 0th element is 1, 0, 1, 2, 3, 4. Oh, I'm adding all of them essentially. So 1 plus 4 is 5, 5 plus 5 is 10, 18 plus 9, 27. So I recognize, oh, this is just taking each element, adding them to the next element until I've gotten to that last element. I don't return 0, I do return that last element if first has gone all the way increased all the way till it's equal to last. So the answer there, 27. The important thing about this is understanding why I got that result. That I see this and I see the plus right there, and I see that mystery. Each time it's going to just add whatever it sees in the position in that array, is going to be adding it to the previous one. This is the same function. Now we're being asked a different question. Let's see here. Uh-oh, I've got a longer array. Are they going to want to make me add all of those together? Man. Well, let's see. Oh, I'm asking for the addition of the elements from positions 4 to position 7. And remember, this first one is at position 0. So let's see. 0, 1, 2, 3, 4. So I'm starting at 13. That's position 4. 4, 5, 6, 7. So I'm adding these 4 together. So 13 plus 15 is 28 plus 18, 46, plus 20 more, 66. You can put that in your calculator, or add it in your head, or put it on paper. Everyone agree the answer is 66? Okay? And see how, again, how I recognize, although it's kind of scary, this big array, remember the 2 parameters, that's where I end the element. This is the element I start with. This is kind of a strange question, a little more philosophical question. If you're building a mission control statement or any program that you want to work and not crash the astronauts, what's the determination? Always use iteration. Always watch out. Any question that has always in it, be suspicious. That's probably not the right answer, because always is usually not the answer. Sometimes always is. But in this case, use the most efficient solution or use a solution that makes the most intuitive sense. To me, they're kind of like the same thing. Like, hey, what makes sense seems like a good answer. But most efficient is probably even more precise on what we're looking for. Most efficient, wouldn't you agree that most efficient is usually makes the most sense? Sometimes if you find something that it's a harder problem, but it is more efficient, you're going to go with it. So C is the best answer. B is close to being the right answer. But C, actually, efficient is the most sense for pretty much any program. Why would you not use the most efficient solution? Unless your goal is to have the most inefficient solution. Like the Rube Goldberg software that you write by accident. We call that spaghetti code. And it happens when you're desperate and you're not sure how it works, and you just try changing things to get the right answer. And most of the time, you just end up in a deep, big hole of spaghetti code. Occasionally, you come to the right answer and you're not sure why. And usually, it's not the right answer. It has a bug in it somewhere that's really hard to find because of all the spaghetti in there. Spaghetti code means code that kind of goes all over the place, no comments to explain what they do, or you have a comment that you put there initially, but then you change the code and the comment is completely wrong. Remember the Fibonacci. This is basically just a review of the Fibonacci. Remember what it starts with is 2 numbers. So how many base cases are there? With the Fibonacci, there's a 2. And they gave a more general case in the book where they have A and B are your first 2 numbers. The classic one is the first 2 numbers are 0 and 1. And I reduced that to if the n is less than or equal to 1, return n. But essentially, there's 2 base cases because it's always adding the 2 previous values together. So 2 base cases. Now, we got to carefully look at this one. I'm taking an integer n. If n ever reaches 0, I'm returning 0. Otherwise, I'm recursing to the previous smaller n, reducing n by 1, and adding it to n times n times n. So the cube of n times n times n, is being added to the next smaller value of n, which will be cubed and then added to the next smaller one, until we hit 0, and I'm returning 0. Okay, so this is one of these times you got to be very careful to look. If I know I eventually return 0, if I'm ever multiplying by recursion, That's going to give me a 0 at that point. Oh, and no, I'm not multiplying by the 0 there. I'm adding that. So I'm adding the cubes all the way down to the value of n equals 0, and that will be 0 added to me. So, and notice here, the order here does not matter. I could have added n times n times n plus, example recursion n minus 1. So, it's not returning 3 times the number. It's returning cubes, not of the number n, because it's adding the rest of them together. So, it's not just the cube of n, it's the sum of the cubes. And it's not even close to Fibonacci, because Fibonacci goes back to the 2 previous values added together. And it has nothing to do with cubes. The same one here, a different question. How many base cases are there? What's the answer? Yeah, 1 base case. I'm only checking when n is equal to 0. Same one again, giving us a number as a parameter, 3. Okay, I get 3. Skip that, it's not equal to 0. 3 cubed plus, okay, 2 cubed, so 3 cubed is 27, 2 cubed is 8, that gives me 35. 1 cubed gives me 1, so I add them together, I should get 36. This one here, same one. Oh, example recursion 0. Oh, easy one. I return 0 when I have n. Don't even worry about what it's doing if I asking for the value at n equals 0. Now, what's that? Yep. Oh, I'm adding the cube. So 3 cubed is 27, plus 2 cubed. 2 cubed is 8. So 27 plus 8 gives me 35. And then 1 cubed is 1. 1 times 1 times 1. So 35 plus 1 gives me 36. The limiting condition. What are the values of n that this is valid for and not recurse forever? Well, the clue here is n is decreasing. So if it's not equal to 0, if it's a negative number, it'll decrease forever because we're past our base case. So n better be greater than or equal to 0. There's our base case. Limiting condition. Now, n greater than or equal to 1 will also not recurse, but it's not covering the exact limiting condition. So these all of these, n greater than 1, n greater than 0, they will keep it from recursing forever, but the precise limiting condition is n is greater than or equal to 0. That's the best limiting condition. That was question 14. So in this case, you can't just look and say, okay, if n is greater than or equal to 1, yeah, it won't recurse forever. That doesn't mean that's the actual limiting condition. It's a satisfying condition, but the exact limiting condition is the n greater than or equal to 0. Now, which one of these? Now you have to think through. Which one of these is invalid? Well, we already know, based on the limiting condition, that it better be greater than or equal to 0. And I can right away jump to seeing that's outside of my limit. I know that is the invalid call. With giving it a negative number, we know that's going to cause infinite recursion. Now this was question 16. That again was probably the tougher one of all these so far. You've got an OR of these two conditions. And if this condition isn't true, I'm recursing to both of these. And so if either of these results in an infinite recursion, I'm in trouble. Now we walked through it at first, but will it help to think through that again to find out what the conditions must exist? Or are you good with what we said the first time? Any confusion about this? Otherwise, I'm going to go on. You good, Brandon? Okay. And the condition was, I hadn't checked in the box, m has to be greater than n, or this will recurse forever. And n must be greater than or equal to 1, because without that, this will recurse forever. That's the short answer. Now again, similar problem, well, the same problem. Which one of these will result in 1 being returned? Well, I know right away, if I have an n equals 1, I'll get 1 returned. And I won't even have to worry about recursing. And if m and n are equal, I know I'm done. So let's just look for that first. Then we don't have to worry about recursing. Well, look at that. I've got 1 with n is 1. I know that this will result in a 1 being returned. So I don't even have to look in more detail. I don't have to calculate the answer for all these unless I want to torture myself. But I'll see that if m and n are not equal, this will go on forever. Even though n finally gets to 1, I've already been recursing, and I have to find the answer for this, which will go on forever because n is not equal to 1. Now getting back to a simpler one, I'm giving m and n only ending when n reaches 0. So m has nothing to do with my end condition. So that's not going to be included in my limiting condition. Because notice, my base case only deals with n. And n is the only thing that's changing as I recurse. That's another way to look at it. So therefore, the limiting condition is n must be greater than or equal to 0. Since m is not in my base case, m has nothing to do with my limit. M can be anything whatsoever. Even though m is in the calculation, m does not affect when I end and stop recursing. Same function. What is the output of 2, 3? Well, we look here. We're taking whatever is in the value m and adding it to whatever this returns. So m is in the calculation every time, and it's the same m each time. And so m is going to be added to another m, added to another m, until when n is 0, I return nothing, and so then nothing gets added to it. So let's think through it. When m is 3, or n is 3, m is 2, 2 plus 2, 2, which will be another 2 plus 2, 1, which is another 2 plus 2, 0. Oh, that returns 0, 2, 2, 2. So 3 2's will be added together. So 6 will be my answer. And I can see now already that the effective function here is basically multiplying m by n. So this is basically thinking of this as a loop. I'm adding m. This is recursing with a smaller n. So I can automatically think in my mind, oh, that's like a loop. As n gets smaller and smaller and smaller, I just keep adding m over and over again. So the general rule statement here is that, yeah, m is, the function is returning m times n. Oh, but now the limiting condition is n greater than or equal to 0. So m times n for n greater than 0. So these are the two possibilities. This one has the correct end, or the limit on n. Back to just a review of Fibonacci. Just remembering from the history, Fibonacci is the sum of the, not the first two, the previous two. Actually, it should have said previous two. The next, yeah, the last two. The third Fibonacci number is the sum of the previous two. Oh, actually, first two. For this one, the general case is the previous two. So, if when we know it is 3, there's the third Fibonacci number here. That is the better answer. The sum of the first two when it's the third Fibonacci number. That's why that's the answer for it. If it just said the Fibonacci number is, but they did say the third Fibonacci number is. Question number 2. All right, zip back there. Yeah, all of them. Do you see all of them as a choice? Okay, so that wasn't the choice last night. I was reviewing these this morning. I realized, wait a minute, A is the answer that he had. So if you only see the 4, go ahead and check A. And I was reading that. I disagreed with the author's answer because he didn't state that only A is the function called. If I could call any of these functions, any of these methods, which typically you can, if they all call each other, I consider them all indirectly recursive. That was question 2. So if you do see all of them as your choice, if you were resuming this, because I changed the answer this morning, or I changed the answer key this morning, and I edited the question, it still shows you the old answer unless you retake the quiz. So if you're just seeing the 4, go ahead and choose A, because that's the next sort of correct answer that the author meant to be the correct answer. But he's missing in the statement. It's not clear enough to make it clear that A is the only indirect, because they all are indirect if they can all call each other. But that doesn't mean they're infinite, because they still may have an ending condition. So which one were we at? 20s or so? 22. Now this one I didn't look. I just knew it took a long, long time, and I'm thinking it's the 10,000 years. Is that the answer? In the book they discussed the Hanoi and how long it would take. I'm just going to check the answer for that because I don't remember from the book. Let me go ahead and just bring up that answer key for that one. I'm pretty sure it's the 10,000. Did they? Let's see. Yeah, it's the 500. Okay, I just knew it was a really big number, and I didn't remember from the book, and I didn't have the book with me when I was reviewing that. So 500 years, and I was thinking the actual manual problem. Back in engineering, that was such a popular problem. We actually had a little Hanoi tower puzzle with 5 discs, and that took plenty of time to solve. But we actually worked through it just for fun. Oh man, we got this far. The rest, there's a lot of true false that are pretty easy, and we are actually past the time, so I'll stop here. But if you have any difficulty with any of those homeworks, just a reminder on the homework, be sure to put header comments in there. Yeah, just when you go back to it, it'll have a button resume previous attempt. If you don't do a final submit, when you come back, it'll let you resume the previous attempt. If you just do save questions, it'll save and then you'll let you resume later. Remember for the assignment, comment headers. I'm looking for good comment headers. Don't forget those. All you need is basically the GUI interface and the recursive class with all the functions in there, with solving those answers for the problems. But be sure to put a function header with a decent description of it. It doesn't have to be super detailed, but just describe and I gave you an example there. All right, have a great weekend. Problem 13, exercise 13 due before Monday. And then we'll be preparing, the last part, pretty easy, loops and things. And then preparing review and get you ready for the final.